All right, so the cool thing about enthalpies and enthalpies of reactions is that we can find tabulated data. So we don't necessarily have to do all these reactions all the time. We can just simply look through a textbook, or really now, all this stuff is online, and find data for experiments without having to do it. Basically, for us, this just means more stoichiometry. So I told you this wasn't going away, and here it is, and we'll see it more throughout the course. You really got to be a master of stoichiometry. And if you understand the concepts and the basics and have a good foundation, really, this isn't too bad. So, for example, in a tabulated data, you might see something like 4 irons combining with 3 oxygens to form 2 iron oxides, right, in this redox reaction. And then you'll see it'll give you kind of a delta H here. And in this case, this delta H is negative 1,652 kilojoules. And then you might be asked a question such as, how much energy is released when 2.00 grams of iron are oxidized into iron 3 oxide. And this is, again, just basically a stoichiometry problem. So like most stoichiometry problems, we want to start with a thing that's not a conversion unit. So we'll start off with our 2.00 grams of iron. And then we think about what we want at the end. We're going to want to get to energy. So we're going to want to get into, some kind of kilojoules or joules or, what have you. And if we think about where we have that piece of information for this reaction, it's right over here, right? And what we can think about this is kind of as per mole of reaction. And so what you can think about is for every, it's just basically conversion units. For this negative 1652, you need 4 moles of iron, or 3 moles of oxygen, or 2 moles of iron oxide, right? You just use the coefficients, just use stoichiometry. So of course, our first step here, since we're starting off with grams, we've got to get to moles, and we can just use the molar mass for that. So the molar mass of iron is 55.845 grams per mole. Now that we're at moles of iron, we can use basically just our stoichiometric coefficients plus this delta H, right? So what this equation tells us is for every 4 moles of iron, we would release negative 1652 kilojoules, right? You see how I described that from the equation, and then stuff just cancels out, and we're left with kilojoules at the end, and we get negative 14.8 kilojoules. Again, what does this negative symbol mean? It means that this reaction is exothermic. So the formation of this iron oxide would release energy. And of course, you can find this, tabulated data. So here's just an example from your textbook, the OpenStax textbook. There's the standard molar enthalpies of combustions. And you can just see, different data points, right? Some reactions are more exothermic than others. In this case, these are all combustion reactions, so they're all exothermic. But obviously, reactions can also be endothermic. Another thing you'll notice is this little kind of degree symbol here. What this degree symbol means is that all of this data is tabulated as what's known as standard state. And that just basically means under certain conditions. So these values are only valid at certain conditions. When you get outside of these conditions, these numbers might change. And generally, this means kind of 1 bar of pressure. If it's a solution, it's generally 1 molar. If it's at a temperature, it's usually 25 degrees Celsius, although that's technically not a requirement of standard state. And you'll see these change a little bit here and there. So don't worry about the degree symbol too much. It just means that these values only hold true under certain conditions. The other thing that you have to be careful of is if you're pulling data from any of these kinds of tabulated tables, you have to be careful with the phase. So for example, if we take hydrogen as a gas, combine it with half a molecule of oxygen, O2, and form water as a liquid, this delta H is going to be equal to negative 286 kilojoules. If we do the same reaction, right, hydrogen as a gas plus half a molecule of oxygen as a gas, but this time we form water as a gas, right? So the only difference between these two reactions is whether the product is in its liquid or gaseous form. We get a different delta H. In this case, this delta H is negative 242 kilojoules, right? It releases less heat because some of that heat was used to form a gas instead of a liquid, which takes more energy. So anyways, the main thing is just be careful with your phases. If you're pulling tabulated data out from the table, make sure that you're pulling out what you're asked for.